Welcome to this coding problem walkthrough. In this session, we'll be diving into problem number 259, 3 some smaller. We'll explore the problem statement, discuss potential approaches, and work through the solution step by step. Let's get started. The problem we are solving is called 3 some smaller. You are given an array of integers called nums and another integer called target. The goal is to find the number of unique triplets within the array, represented by indices I, j, k, that satisfy two conditions. First, the indices must follow the order 0 equals I less than j less than k less than n, where n is the size of the array. Second, the sum of the values at these indices, nums I plus nums j plus nums k, must be less than the given target. For the input, you will receive the array nums and the integer target, and the output should be an integer count indicating how many such triplets satisfy these conditions. This problem requires careful consideration of both the input format and the constraints to ensure an efficient solution. Let's look at an example to understand this problem better. Consider the input where nums is -2, 0, 1, 3, and target is 2. Here, the output is 2. This is because there are exactly two triplets in the array that meet the conditions. The first triplet is -2, 0, 1, where the sum is -2 plus 0 plus 1 equals -1, which is less than 2. The second triplet is -2, 0, 3, where the sum is -2 plus 0 plus 3 equals 1, which is also less than 2. No other combinations of three numbers in the array satisfy both conditions, so the result is 2. Now, let's examine a couple of additional examples to clarify edge cases. In the first example, the input nums is an empty array, and target is 0. Since there are no elements in the array, it is impossible to form any triplets. Therefore, the output is 0. In another example, where nums contains only one element, such as 0, with target again being 0, there still aren't enough elements to form a triplet. As a result, the output is also 0 in this case. Finally, let's consider the constraints and edge cases that are critical for solving this problem. The length of the nums array can range from 0 to 1000, which means the solution must handle both very small and relatively large arrays efficiently. The values within nums can range from -100 to 100, and the target can vary between -10000 and 10000. Special cases to handle include empty arrays and arrays with fewer than 3 elements, where the result should always be 0. Additionally, the solution must be able to process negative numbers and ensure it works efficiently within the provided constraints. To tackle the problem of finding triplets whose sum is smaller than a given target, we first consider the brute force approach. This method involves iterating through all possible triplets in the array by using 3 nested loops. For each combination of indices, we calculate the sum of the 3 numbers and check if it is less than the target. If it satisfies the condition, we increment a counter. While this approach is simple and intuitive, it has a significant drawback: its time complexity is n cubed, which makes it highly inefficient for large arrays. The 3 nested loops mean the runtime grows cubically with the size of the input, making it impractical for competitive programming or real-world use cases where performance is critical. Now, to address the inefficiency of the brute force method, we turn to an optimized two-pointer approach. The first step in this method is to sort the array, which allows us to leverage the sorted order for efficient pair identification. Once sorted, we fix one number in the triplet, starting with the first element. Using a loop, this fixed number becomes the foundation for pairing. We then use 2 pointers, one starting just after the fixed number and the other at the end of the array. The idea is to calculate the sum of the fixed number and the pair of numbers pointed to by the 2 pointers. If the sum is less than the target, it means all the pairs between the current left and right pointers are valid since the array is sorted. We can then add the count of those pairs to our result and move the left pointer forward. On the other hand, if the sum is greater than or equal to the target, we decrement the right pointer to try smaller numbers. This approach drastically reduces the number of combinations we need to consider, bringing the time complexity down to n squared. An alternative approach to the problem uses binary search. Like the two-pointer method, it starts by sorting the array. Here, we fix the first number in the triplet and iterate over the second number. For each pair of fixed numbers, we use binary search to find the largest index where the sum of all 3 numbers is still smaller than the target. The number of valid triplets for that pair is then calculated as the difference between the binary search result and the index of the second number. While this method achieves a slightly better theoretical efficiency for very large arrays, with a complexity of O(n squared log n), it introduces additional complexity in the implementation. The binary search logic can be harder to grasp and debug compared to the straightforward two-pointer technique, making it less intuitive for many developers. Ultimately, the optimized two-pointer approach emerges as the most balanced solution for this problem. It offers a significant improvement over the brute force method by reducing the complexity to O(n squared, while maintaining simplicity and clarity in implementation. While the binary search approach is interesting from a theoretical perspective, it adds unnecessary complexity without providing a significant performance advantage for most scenarios. The key insight, or aha moment, in this problem comes from recognizing that sorting the array allows us to leverage the two-pointer technique to efficiently count valid triplets. By calculating the number of valid pairs directly, rather than iterating through each one, we save time and keep the solution elegant. In conclusion, the two-pointer method strikes the best balance between efficiency, simplicity, and practicality, making it the optimal choice for solving this problem. The problem we're tackling here asks us to count the number of unique triplets in an array such that the sum of the three numbers is strictly less than a given target. To solve this, we can start with a simple brute force approach. First, we need to ensure the input is valid. If the array has fewer than 3 elements, it's impossible to form a triplet, so we can immediately return 0. Next, we iterate through all possible combinations of triplets using 3 nested loops. The outer loop picks the first number, the middle loop picks the second number, and the inner loop picks the third. For each combination, we calculate the sum of the 3 numbers and check if it's less than the target. If it is, we count that triplet as valid by incrementing a counter. This straightforward method ensures we consider every possible triplet in the array. To ensure our brute force algorithm is robust, we must handle a few edge cases. For example, arrays with negative numbers should still work correctly since addition naturally handles both positive and negative values. Additionally, the order of indices, where I is less than j and j is less than k, ensures that we don't count the same triplet multiple times. Once all triplets have been evaluated, we return the final count of valid triplets. The pseudocode here outlines this approach in a concise way. It starts by checking if the array has fewer than 3 elements. If not, it iterates through the array using 3 nested loops, checking the condition for each triplet and updating the counter if the condition is met. Finally, it returns the counter, giving us the total number of triplets that satisfy the problem's requirements. While the brute force approach is simple and guarantees that all triplets are considered, it has significant limitations. With 3 nested loops, the time complexity is O(n cubed, which becomes impractical for large arrays. For instance, if the array size exceeds 10,000 elements, the number of iterations grows exponentially, making the approach too slow. However, this approach also highlights opportunities for optimization. By sorting the array, we can reduce redundant computations and explore smarter traversal methods. For example, instead of using 3 loops, we could use a two-pointer technique to check for valid triplets more efficiently. Importantly, handling edge cases like duplicates or negative numbers does not require extra effort here since these are naturally addressed by the constraints we've defined. Let's take a moment to focus on the data structures and operations involved in this problem. The array itself, nums, is central to our solution as we derive all triplets directly from it. If we choose to optimize, sorting this array becomes a key step in reducing computational overhead. As for tracking results, a simple integer variable, count, is used to keep a running total of valid triplets. The brute force approach relies heavily on triple nested loops to explore all combinations, ensuring no triplet is missed. The condition check, nums, I, plus nums, j, plus nums, k, target, acts as a filter to identify and count only the valid triplets. Finally, incrementing the counter ensures we accurately tally these results. These basic operations are essential for both the brute force and optimized approaches. To address the inefficiencies of the brute force method, we can turn to an optimized approach. First, sorting the array simplifies the problem by allowing us to use structured traversal methods. Once sorted, we can fix one element and use a two-pointer technique to efficiently find the other 2 elements that form valid triplets. This method eliminates the need for the innermost loop, significantly reducing the computational complexity from O, n cubed, to O, n squared. This optimization makes the solution much more scalable, especially for larger arrays. In the next steps, we'll dive deeper into how this two-pointer technique works and how it transforms the problem into a more efficient computation. This Python implementation solves the three-sum-smaller problem using the two-pointer approach for optimal performance. First, the input array nums is sorted in non-decreasing order, ensuring that the two-pointer technique will work efficiently. The main loop iterates through each element of the array, treating it as the first element of the triplet. For each I, two pointers are initialized, left immediately after I, and right at the end of the array. The sum of the triplet, nums, I, plus nums, left, plus nums, right, is computed. If this sum is strictly less than target, all combinations between left and right are valid since the array is sorted. The count of such triplets is incremented by right-left, and left is moved forward. If the sum is greater than or equal to target, the right pointer is decrement to attempt a smaller sum. The algorithm continues until the two pointers meet, ensuring all valid triplets are counted. This approach has a time complexity of O, n squared, making it suitable for reasonably large inputs while being more efficient than brute force. The final result is the total number of triplets satisfying the condition, returned by the function. Here, we start by importing the necessary library, arrays, which we'll use to sort the input array. In the three-sum-smaller method, the array is sorted first to take advantage of the two-pointer approach, a common technique in problems like this. Then, we initialize a variable count to keep track of the number of valid triplets that satisfy the condition. Next, we iterate through the array using a for loop, where the variable I represents the first element of the triplet. For each I, we set up two pointers, left starts just after I, and right begins at the end of the array. These two pointers will help us efficiently find all valid combinations. Inside the while loop, we calculate the sum of the current triplet using nums, I, nums, left, and nums, right. If this sum is less than the target, it means all combinations between the left and right indices are valid, so we increment count by the difference, right-left, and move the left pointer forward to check the next potential triplet. If the sum is not less than the target, we decrement the right pointer to reduce the sum and continue searching for valid triplets. Finally, after the for loop completes, the method returns the total count of valid triplets that satisfy the condition. This marks the end of our implementation. The logic is efficient because sorting the array and using the two-pointer technique significantly reduces the number of comparisons we need to make. With this approach, we achieve a time complexity of O, n superscript 2, which is optimal for this type of problem. The code is now ready to handle any input array and target value, as long as the constraints are met. To solve the three-sum-smaller problem, we begin by working through an example where nums is 1, 2, -1, -4, and the target is 2. The first step is to sort the array. Once sorted, nums becomes -4, -1, 1, 2. Sorting ensures the elements are in ascending order, which simplifies the two-pointer approach we'll use later. Next, we initialize a variable, count, to 0. This will keep track of the number of triplets whose sum is smaller than the target. Finally, we start iterating through the array using the first pointer, I. This pointer will represent the first number in each potential triplet. By controlling the first pointer, we can systematically explore all possible combinations of three numbers in the array. When I is 0, nums, I, is -4. We set the left pointer to index 1 and the right pointer to index 3. This gives us the triplet consisting of nums, I, nums, left, and nums, right. We calculate the sum of this triplet, which is -4 plus -1 plus 2, resulting in -3. Since -3 is less than the target of 2, all pairs between left and right are valid. This means we add the difference between right and left, which is 2, to our count. The count is now 2. We then increment the left pointer to 2 and calculate the new sum, -4 plus 1 plus 2, which is -1. Again, -1 is less than 2, so we add 1 more to the count, making it 3. After incrementing left again, left becomes equal to right, so we stop processing for I equals 0. Next, when I is 1 and nums, I, is -1, we set left to 2 and right to 3. The sum of this triplet is -1 plus 1 plus 2, which equals 2. Since 2 is not less than the target, we decrement right to 2, and the loop ends as left is no longer less than right. The final count for this example is 3. In the second example, nums is 0, minus 2, minus 1, 3, and the target is 2. After sorting, nums becomes -2, minus 1, 0, 3. We initialize count to 0 and start iterating with the first pointer. When I is 0 and nums, I, is minus 2, we set left to index 1 and right to index 3. The sum of the triplet is minus 2 plus minus 1 plus 3, which equals 0. Since 0 is less than 2, we add the difference between right and left, which is 2, to count. The count is now 2. Next, we increment the left pointer to 2 and calculate the sum again, which is minus 2 plus 0 plus 3, resulting in 1. Since 1 is still less than 2, we add 1 more to the count, making it 3. Incrementing left to 3 ends this iteration because left is no longer less than right. Now, when I is 1 in nums, I is minus 1, we set left to 2 and right to 3. The sum of the triplet is minus 1 plus 0 plus 3, which equals 2. Since 2 is not less than the target, we decrement the right pointer to 2. At this point, left is no longer less than right, so the loop ends for this value of I. The final count for this example is 3. Moving on to a third example, where nums is 3, 1, 0, minus 2, and the target is 4, we again begin by sorting the array. Once sorted, nums becomes -2, 0, 1, 3. We initialize count to 0 and proceed to iterate through the array. For I equals 0 and nums, I equals minus 2, we set left to 1 and right to 3. The sum of the triplet is minus 2 plus 0 plus 3, which equals 1. Since 1 is less than 4, we add the difference between right and left, which is 2, to count. The count is now 2. Incrementing the left pointer to 2, we calculate the new sum, minus 2 plus 1 plus 3, which equals 2. Since 2 is still less than 4, we add 1 more to the count, making it 3. Incrementing left to 3 ends this iteration. For I equals 1 in nums, I equals 0, we set left to 2 and right to 3. The sum of the triplet is 0 plus 1 plus 3, which equals 4. Since 4 is not less than the target, we decrement right to 2. At this point, left is no longer less than right, so the loop ends. The final count for this example is also 3. To analyze the time complexity of our algorithm, let's first break it down into its key components. The first step is sorting the input array, which takes O, n asterisk log, n, time since most efficient sorting algorithms, like timsort, operate in this range. Next, we have the outer loop, which iterates from the start of the array up to the third to last element. This means it makes approximately n 2 iterations, contributing O, n, to the time complexity. Finally, within each iteration of the outer loop, we use the two-pointer technique. This involves a single pass through the subarray, which is also O, n. Combining these, the two-pointer logic runs O, n, times for each of the O, n, iterations of the outer loop, resulting in O, n squared, time complexity for this part of the algorithm. Now, let's combine the complexities of the different steps to compute the total time complexity. Sorting the array contributes O, n asterisk log, n, while the outer loop combined with the two-pointer logic contributes O, n squared. Since O, n squared, grows faster than O, n asterisk log, n, as the input size increases, it dominates the total complexity. Thus, the overall time complexity of the algorithm is O, n squared. This indicates that, for large arrays, the two-pointer logic is the key driver of the algorithm's runtime. Next, we analyze the space complexity of the algorithm. Sorting the array is performed in place, using algorithms like timsort, which require O1 auxiliary space. Additionally, the algorithm doesn't rely on extra data structures like arrays or hash maps. Instead, it uses only a few variables and pointers to track indices and perform calculations. Since the memory usage does not scale with the size of the input, the total space complexity is constant, or O1. This makes the algorithm highly efficient in terms of memory usage. Let's delve into the best, average, and worst-case scenarios for this algorithm. In the best-case scenario, the input array is already sorted, but the time complexity remains O, n squared, because the two-pointer logic still iterates through the subarray for each element in the outer loop. The average case also results in O, n squared, as the algorithm evaluates all possible triplets across the array. Similarly, in the worst case, the algorithm must process all triplets, maintaining the O(n)² complexity. The sorting step remains O(n)log n in all cases, but it does not dominate the overall complexity. Compared to a naive approach that relies on 3 nested loops, which would take O(n)³ time, our algorithm is a significant improvement. The two-pointer technique eliminates the innermost loop, reducing the complexity from O(n)³ to O(n)². To further justify this mathematically, consider the naive approach where, for each element in the array, all pairs in the subarray are evaluated. This results in O(n)³ combinations. The two-pointer technique optimizes this by processing multiple pairs in a single pass, reducing the complexity to O(n)². In summary, the algorithm achieves a time complexity of O(n)² due to the combination of the two-pointer approach and the outer loop. The space complexity remains O(1), as no additional memory is used beyond the input and a few variables. This optimized O(n)² complexity makes the algorithm far more efficient than the naive approach, particularly as the input size increases. One of the most common mistakes in solving the 3-sum smaller problem is using 3 nested loops to iterate over all possible triplets. While this brute force method is straightforward, it becomes highly inefficient for larger arrays due to its O(n)³ time complexity. A better approach is to use optimized techniques like sorting and the two-pointer method. Speaking of sorting, another frequent error is neglecting to sort the array before applying the two-pointer approach. Sorting is crucial because the two-pointer method depends on the array being in order to function correctly. Additionally, off-by-one errors, such as starting the second pointer at the wrong index, can lead to unnecessary iterations or incorrect results. Developers should also be cautious of edge cases, such as handling arrays with fewer than 3 elements, empty arrays, or situations where no triplet satisfies the condition, as these oversights can result in crashes or incorrect outputs. Another common pitfall is misinterpreting the problem requirements. For instance, misunderstanding strictly less than target as less than or equal to target can completely derail your solution. It's essential to carefully read and clarify the problem statement to avoid such errors. Sorting the array is not just a recommendation, it's a critical step that simplifies the problem. By sorting, you can leverage the two-pointer approach, which reduces the time complexity from O(n)³ to O(n)². This optimization is often necessary to meet time constraints in coding interviews. To further improve efficiency, look for opportunities to avoid redundant work. For example, if the smallest possible triplet sum with your current index is already greater than the target, you can skip further iterations for that index entirely. When explaining your approach in an interview, it's important to communicate the trade-offs you've made. For instance, justify why sorting, despite its O(n)log n cost, is ultimately beneficial or why brute force isn't practical for larger inputs. In coding interviews, discussing edge cases demonstrates thoroughness. Bring up scenarios like arrays with fewer than 3 elements, empty arrays, or situations where no valid triplet exists. Clearly state how your solution handles these cases to show your attention to detail. Additionally, understanding related problems can deepen your grasp of the 3-sum smaller problem. For example, the 3-sum problem requires finding unique triplets that sum to 0, while 3-sum closest focuses on finding the triplet with the sum nearest to a target. Extending this concept, the 4-sum problem involves quadruplets instead of triplets. Lastly, 2-sum, one of the most foundational problems, introduces pair-based approaches that are often expanded into these more complex variations. Recognizing these connections helps in adapting techniques across similar challenges. There are multiple approaches to solving this problem, each with its own advantages and trade-offs. The brute force approach, with its O(n)³ complexity, is simple to implement and easy to grasp. However, it becomes impractical for larger inputs and often fails time constraints when n exceeds 100. A more efficient method is the two-pointer technique, which, after sorting the array, achieves an O(n)² complexity. This approach is widely used in problems like 3-sum but requires the initial sorting step, adding an O(n)log n overhead. Additionally, it doesn't generalize well to problems with larger sums, like 4-sum or k-sum. Another option is the hashing-based approach, which also achieves O(n)² complexity but requires extra memory for hash tables. This method can be helpful in variations of the problem, such as counting the number of triplets that meet certain criteria. However, it can complicate the handling of duplicates, so it's important to weigh the additional complexity against its benefits. Great job working through this problem. In this conclusion, we reviewed the key algorithms, takeaways, and complexities. Remember to practice regularly and challenge yourself with similar problems. Thank you for watching, and don't forget to like and subscribe for more content. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!